Okay, we're going to continue our discussion on isotopes, and this is just the beginning of the PowerPoint. I decided to present it like this instead of normal, so I could write on sheets and do some work for you guys. So let's dive right into it. So the first question says, what is an isotope again? Which we've already looked at, but let's look at it in terms of the actual word, taking the word apart. So the Greek prefix iso stands for same, or means, oh, I don't want to do this, same. And tote means place. And it makes sense because if you look at an isotope on the periodic table, it's all going to be in the same place because lithium, you'll find, is the same place on the periodic table. It's going to be somewhere over here that you can't see on my camera. There it is. There's lithium. Okay. So how do isotopes form? Um, Unstable elements naturally are forced to form in the lab, and that's nuclear chemistry. So that's it. There are some naturally occurring isotopes, and that just means that the element's just unstable and over time just starts to deteriorate. So then the question says, are all isotopes for an element the same? And the answer to this is no, because they have different abundances. What that means is kind of like your grade, you do the weighted averages. So your test and your labs are the same weighting, but if I were to compare like your test and quizzes, they don't have the same weight. And it's the same thing, like some isotopes there's more of them than other ones, so they get more weighting. That's essentially what that means. Okay. I like this little poem I found because, well, it's chemistry and it's not isotopes, but if you read it carefully, it's kind of a misnomer. So it says isotopes, diamonds like fate bright and fine. Break it once, it'll break you twice. Dark like coal, not perfectly nice. Burn it coal will still warm you like a sacrifice. So kind of dark here, but it talks about two substances, kind of implying that they're isotopes, diamonds and coal. Well, we both know we know that they're both made of carbon, but are they isotopes? No. These guys, they're both made of carbon, but carbon's just in different forms. These are called allotropes. So somebody that didn't know chemistry wrote this poem. The arrangement of atoms is just different in allotropes. That's all. So sadly, somebody did not know chemistry. Okay, I would take a minute and let's take a look at defining some terms here. We talked about this in the last group, average atomic mass. It's the weighted average of the atomic masses of the naturally occurring isotopes of the element. That's why I'm looking right now. We already had that. I'll say it one more time though. It's the weighted average of the atomic masses of the naturally occurring isotopes of an element. Relative abundance, I'm going to write this here, is the average value for the isotopes of an element and takes into account the relative abundance of the isotopes. Remember the number of protons plus neutrons. And this thing, I'm going to put here C Pogel because we're going to do a Pogel on this in a minute. Okay, I just want to be able to move there. Okay, isotopic notation. Again, we looked at, but we did not see it. We saw this nucleotide arrangement, but we didn't see it in this arrangement. Both of these are typical isotope ways to write them. So let's do protons, neutrons, and electrons for each of these. So if I look at silicon on the periodic table, I have Si, and it says, it's right here. So we have 14, and we have 28.086. So this number right here is replacing this mass. So you use 29 instead of 28. So we still have our protons is 14. Our neutrons is now 29. I'm going to write here so you guys can't go 29 minus 14. So I just give it 15 there. And then our electrons is the proton number same, it's 14. In this format, let's do protons, neutrons, electrons. Protons still 14. Neutrons, we're going to subtract these. So again, 29 minus 14 is 15. And electrons, 14. So just two different ways to show isotopes. Just be familiar with it. Okay, now we're going to start looking at relative abundance and average atomic mass and how we use them. So I'm going to show you how to do this calculation. It's not too bad. So the formula is the average atomic mass is equal to the weights that they give you, the mass that they give you, mass times the percent, we make the percent a decimal. So, but I'll put percent decimal, and then we're going to have them. So let's see more than one. So I'm going to show you that one. So let's do this. There are two isotopes of gallium. Gallium 69, gallium 71. The relative abundances are 60.10 and 39.89 respectively. Is the average atomic mass of gallium closest to 69, 70, 70? Okay, so we're solving for the average atomic mass. So I'm going to say AA equals, and I'm going to do the math here. So this is the first one, 69 times percent, but we're going to make it a decimal. So 0.600 plus 71 times 0.3989. And when I calculated that, I got 69.79. So I would say the answer should be 670. So no big deal. So that's what we do calculate relative abundances. And this page is similar, very similar problems. A couple are just a little harder. So I'm going to do one with you, and then I'll let you guys do the rest for practice. Okay, so let's look at the lithium one. Lithium has an elemental atomic mass of 6.941 and has two naturally occurring isotopes. Their masses are blah, blah. What are the two natural abundances to two decimal places of the isotopes of lithium? So they already told us the average mass. So we're going to set this equal to 6.941. That's what they said it is equal to, and I don't know what the masses are. Like the other one told us. I'm sorry, we don't know what their abundances are. We know their masses. So we can multiply their mass, 6.0151 times x, we don't know, plus, we're going to say 1 minus, and I'll explain this in a second, x times, what's the other one? 7.0160. So remember, this has to add up. They have to, percentages have to add up to 100. So that's why I'm doing the 1 minus, because I know that whatever this one is, the rest of this has to be 100. And remember, making a percent and decimal, we're changing it. So that's why it's coming out to that. So when I solve for x here, I get that x equals 0.0749. And if I'm changing that to a percent, it's 7.49 But then the question said, so that's for the 6, right? The 6 of the thing. But then the 7 is whatever's left. So I have 100 minus that x. So 100 minus 7.549, and I'm going to get 92.451%. So and that's 7 kilowatt. Okay. All right. Try the other two and see how you guys can do on that. Okay. Another way they can show it is using mass spectroscopy.